In this presentation, we will review how to create matrices in MATLAB, as well as to how to extract elements from them. Numbers can be grouped together in data structures called arrays. In MATLAB, arrays are typically referred to as matrices, and they can have an arbitrary number of dimensions. When elements are organized in a row, we call this a row vector, and when elements are organized in a column, we call this a column vector. You can represent virtually anything in arrays. For example, each box could store a voltage value at different time points. When arrays have two dimensions, that is, multiple rows or multiple columns, we call this a 2D matrix. You could use a 2D matrix to store a heat map of locomotion or neuronal activity at a given time point. And if you wanted to represent those data across time, you could use a 3D matrix. A common use of a 3D matrix is to represent images. In this case, each element is the intensity of a pixel with x and y coordinates, and each layer of the 3D matrix represents a color or a channel. For example, red, blue, and green if the color space is RGB. And then a fourth dimension would be required to represent time. All these arrays, regardless of size, are considered matrices in MATLAB, including one with a single element or one with no elements at all. To create a row vector, separate numbers by commas and enclose them with square brackets. Place a semicolon at the end to suppress the output of this definition on the command line. Use the function disp to display the vector. All these elements are numeric or of type double, hence they can be organized together in matrices. Now, to create a column vector, separate numbers by new lines. You can also separate numbers by semicolons and enclose them with square brackets. To create a 2D matrix, separate rows by semicolons. Alternatively, you can write one row per line and the semicolon after each row is optional. To get the size of a matrix, use the function size. Here, matrix 2 has 2 rows and 3 columns, as it was just defined. MATLAB has built-in functions to create matrices, and they are all called in a similar way. Option 1, by passing a row vector with sizes for each dimension, note the square brackets, or option 2, by passing each of the sizes as a separate argument to the function, note the lack of square brackets. The returned value, that is the function output, is a matrix with the requested dimensions, each element set to one thing or another according to the function being called. An example of these functions is the function zeros. While we can pass arbitrary number of dimensions to it, let's focus on 2 dimensions for now. The first element is the number of rows, and the second is the number of columns. After executing this in the command line, we get a column vector with 3 elements all set to 0. Similarly, we can make a row vector with zeros by setting the dimensions to 1 row and 3 columns. If the number of rows and the number of columns are both greater than 1, then we get a 2D matrix. A 2D matrix is not different than a 3D matrix, except the size for the third dimension is set to 1. Here's how a 3D matrix looks like. We can represent here a color image with 9 pixels. And while you may not necessarily be able to picture an n-dimensional matrix, it can still be represented in MATLAB. Another thing to note with these functions is that MATLAB will return a square matrix when you provide them with only one size. So when creating rows or columns, it is necessary that you write either 1, n or n, 1. Other built-in functions to create matrices are zeros, which we just reviewed, ones, true, rand, and nan. Another way to create matrices is using the colon operator. In the simpler form, the syntax is from, to. This creates an array with elements separated by 1. To specify a different step, the syntax is from step 2. For example, let's increase from 2 to 10 in steps of 2. We can also provide a step of 1, which gives the same result as the first test. The step does not need to be an integer or a positive number. To get a decreasing array, we type the larger number first, followed by a negative step, and finally the ending value. Note that the array stops at 2, not at 1, as the colon operator is designed not to go beyond the ending value. Since the default step is a positive one, we must not ignore the step when creating an array with decreasing values, otherwise we will get an empty array. Finally, there is a function equivalent to the colon operator. It takes 3 arguments, from, step, and 2, and produces the same results as the colon operator. Another function to create vectors is linspace. It is similar to the colon operator, except instead of providing the step, you provide the number of parts. For example, create an array with 5 elements ranging from 0 to 360. We can accomplish the same result with the colon operator if we know the step, which in this case is 90. There are several ways to extract values from matrices in MATLAB. Let's start by defining a vector with 3 elements. Knowing the position of an element in an array, we can extract it by writing the name of the variable followed by the position enclosed by parentheses. The first element is 1, the second element is 2, and so on. The last element can also be called using the keyword end, and the second to last one end -1, and so on. Just make sure the index does not exceed the number of elements in the array, otherwise you will get an error. As you can see, this indexing works in a very intuitive way for 1D arrays, that is, row or column vectors. Let's now create a 3 by 3 matrix. The first element is 1, as expected. The second element, though, is 4, not 2. And this is because MATLAB indexes 1 column at a time, from top to bottom. It follows that the third element is 7, and the fourth is 2. Similarly, the last element of this matrix is 9. Multiple elements can be extracted at once by using arrays of indices. It is still considered one subscript except with multiple indices. The first and third elements of M are 2 and 6. The elements 1, 2, and 3 created with the colon operator are 2, 4, and 6. This is equivalent to using the keyword end in place of 3. Or we can use a shortcut to all elements by simply placing the colon operator by itself. Note, however, how the colon operator by itself turns the values into a column vector. We can also include the end shortcut in the indexing array, and indices can repeat or appear in any order. We can also first define an array of indices and then use it to index an array. However, the keyword end cannot be used here as an index because it's outside the indexing statement. Finally, if the indices are arranged as a matrix, let's say elements 1 through 4 organized as a square matrix, then the shape of the output will have the same shape of the indexing array. An easier way to extract elements from matrices of 2 or more dimensions is with multiple subscripts, one for each dimension. Each subscript refers to positions in one dimension, for example, row, column, etc., and you can think of the combination of these subscripts as coordinates in the array. So the first subscript moves vertically to point to rows, the second moves horizontally to point to columns, and the third one moves inwards, if that makes sense, to point to layers, and so on. Let's create a matrix. In the position 1, 1, there's 1. In the position 1, 2, there's 2. Note, we can also say In the intersection of the second row and the first column, there's 4. In the intersection of the last row and the last column, there's 9. In the intersection of the second row and the last column, there's 6. The most complex variation of this indexing method is using multiple indices in multiple subscripts. In other words, extracting multiple elements at once by intersecting several coordinates in multiple dimensions. This is easier to understand with an example. First, let's define a 2D matrix. To get elements 10, 20, and 30, select the first row, that is number 1 in the first subscript, and columns or elements 1, 2, and 3 in the second subscript. Alternatively, select the first row and all columns. To select elements 30 and 60, intersect rows 1 and 2 with the last column. We can reorder columns by leaving rows unchanged and choosing columns in a specific order. We can reorder rows by choosing rows in a specific order and leaving columns unchanged. And we can, of course, combine these two operations. The last way of indexing that I will talk about is using logical masks. Logical masks are like switches. They are either on or off, true or false. First, create a logical array by asking MATLAB which elements in M are larger than 2. If you use this logical array in M, you get the expected elements 4 and 3 in positions 1 and 4. Mask is a logical array, and even though MATLAB shows it filled with zeros and ones, they are not the typical zeros and ones. Indeed, you may not use zeros at all to index any array. To recreate this special type of zeros and ones, we type the keyword true or false instead. Logical arrays are very useful and a whole topic on their own, so we will learn more about them in a different lesson. A few things left to mention about logical indexing. You may index fewer elements than the target array, but you may not index with more true elements than the target array. Finally, the mask can be a 2D matrix, but the resulting operation will be a column vector because MATLAB indexes one column at a time, from top to bottom. However, if the mask is a vector, your output will have the same shape of the vector. That is, a row mask produces a row vector and a column mask produces a column vector.